In remark 1.3 in Jostein's notes, we assume a slightly modified version of the chain ladder assumptions. This implies that the standard chain ladder function assumptions CL1 and CL2 still hold, whereas the third one will turn out slightly modified. So we still have independence across accident years. And we also still assume that the expectation of the total claims for the next development year, given the information of the observed development years, is equal to Fj multiplied by Cij. However, the last chain ladder assumption is slightly modified because we assume that the variance of the upcoming total claim, given the information from the previous development years, is now written as sigma j squared multiplied by Cij squared. Before, we didn't have the square on the Cij. So we assume a slightly modified set of chain ladder assumptions, and furthermore, we now assume that there exist positive weights AI such that we can estimate these Fj coefficients using a weighted sum of the development ratios, where the development ratios are defined accident year by accident year for each development year, given as the next year's total claims divided by the present year's total claims. We furthermore impose that this estimator is indeed an unbiased estimator of Fj. And this restriction is actually very nice because it allows us to be a bit more specific about which values AI can take. Because if we try to calculate the expectation of this estimator given epsilon j, then what we see is it boils down to calculating the conditional expectation of Fij, which is given as Cij plus 1 divided by Cij. Now, since Cij is measurable with respect to the sigma algebra epsilon j, we can just take out the Cij. And inside the conditional expectation, what you have left is the mean of Cij plus 1 given epsilon j, which by our second chain ladder assumption is equal to Fj multiplied by Cij. So this Cij cancels with this Cij. And now we have that Fj multiplied by the sum of the AIs is required to be equal to Fj by this restriction up here. And we can now conclude from this restriction that we must require the sum of the A's to be equal to 1. So we require the weights to sum to 1, which also makes sense in a way, because if you want to estimate this ratio here, then it makes sense to do so by preserving the scale, at least, of the development ratios. So we have this assumption here, and what we now want to do in the exercise, goal is to find the AI which minimize the conditional variance of the estimator in order to show, in order to obtain the estimator f hat j equal to 1 divided by I minus j multiplied by the sum of Fij over all the accident years. So what have I written up here? What I've written up is that we wish to minimize the variance of this estimator, and we wish to more specifically find those weights which minimize this variance and show that then the estimator will be given as the simple average of the development ratios. So essentially, we just want to show that each AI should be chosen as 1 divided by capital I minus j. So we want to find those AI that minimize the variance of the estimator. So let's just calculate an expression for this variance. Plugging in the definition of the estimator, we have the variance of the sum of AIs multiplied by Fij conditioned on epsilon j. Now, due to the first chain ladder assumption, we have independence across accident years, which means I can take out the sum, and then the scaling constant AI can be taken outside of the variance as well, as long as I square it. So we have the sum from 0 to I minus j minus 1 multiplied of AI squared multiplied by the conditional variance of Fij given epsilon j. Now, the development ratio Fij is defined as such. So the variance of Fij given epsilon j is equal to the variance of this ratio of the total claims given epsilon j. The total claims for development year j are actually measurable with respect to epsilon j. So I can take 1 over Cij outside as long as I square it, and what I have left is then the variance of the total claims for year j plus 1 given epsilon j. By our chain ladder assumption, that has the value sigma j squared multiplied by Cij squared. And now this cancels with this, and that leaves us with sigma j squared. Okay, so we've established that this conditional variance is just sigma j squared. And therefore, our estimator conditional variance is just the sum of the squared weights multiplied by sigma j squared. And we would like to find those AI which minimize this sum. Now here we actually have a slight problem. And the reason I say that is because, well, the AIs that minimize this expression are just AI equal to 0. If you set all of the AIs equal to 0, then this expression is minimized and equal to 0. But that isn't very helpful. What we need to recall here is that we have a constraint. Recall the constraint that we have placed on the sum of the AIs. We have required that the weights must sum to 1. And that is a constraint that is very useful because that means that AI equal to 0 does not solve our problem. So we would like to minimize this thing here. But with respect to the constraint that the AIs must sum equal to 1. What we're going to do now is use a little trick called the method of Lagrange multipliers. If that's a bit rusty, you can Wikipedia it. So essentially what we do is we subtract the 0 in our expression, where that 0 in the expression is given as the sum of the weights minus 1. And then we multiply this by the Lagrange multiplier lambda. Then we just go forth, as we typically do, by finding the partial derivative with respect to what we want to minimize this in. So the partial derivative with respect to AI is then given as sigma j squared multiplied by AI multiplied by 2 minus, and well, what you have here, the derivative of this is just 1, so it's minus lambda multiplied by 1 because it's only the term with the specific AI that yields a derivative 1. All the other terms just vanish. And our question now is, when is this equal to 0? Well, this is equal to 0 if and only if AI is equal to lambda divided by 2 sigma j squared. Now this is quite interesting because we have reached an expression now where you can see that AI is equal to some value, where we'll have to determine what lambda can be, but it is equal to some value, which is a number which does not depend on I. It does not depend on I. No matter which AI we use here, we reach the same conclusion. And what that means is that the sum of the AIs is also exactly, well, since the sum of the AIs is equal to 1, then as long as you know how many AIs there are, then you can also determine what the value of each AI is. So AI is a number which does not depend on I. Hence, A1 is equal to A2 is equal to A3, and so on and so on. Oh, we also have an A0. And that is equal in the end to AI minus J minus 1. Combined with the fact that they sum to 1, we see that AI is just equal to 1 divided by the number of terms we have in the sum, or by the number of AIs we have, and we have I minus J weights. So we see that AI equal to 1 divided by I minus J minimizes the conditional variance of F tilde J. And in conclusion, the new version of this estimator can then be written up with AI equal to 1 divided by I minus J. There we go. And we are done. And as you've probably noticed, what I said during exercise sessions did not make sense. It is the assumption in this exercise that we can write the estimator of Fj using a weighted sum of the development ratios. And it is the conclusion that if we change the chain ladder assumptions a little bit, then it is possible to choose those weights such that we just estimate Fj by taking the average of the development ratios.